Hello guys. Okay, we are already at chapter 5. Chapter 5, crystal vibrations. In this lesson, we are going to learn how atoms move inside a crystal and why that tiny motion is very important in solid state physics. Even though a solid looks rigid and still from the outside, the atoms inside are not completely still. The atoms actually vibrate around their fixed positions. So these small vibrations help us to understand many physical properties of materials, including sound. Sound propagates inside any materials, the heat, and thermal behavior. So in this chapter, we will start from a very simple picture and slowly build toward more useful models like phonons, the Einstein model, and the Debye model, which I have shown to you this morning. And please do not worry if some of the diagrams or equations looks unfamiliar. For this class, our focus is understanding the ideas clearly and not memorizing difficult mathematics. And before we begin, let us look at what you are expected to learn in this chapter. By the end of the lesson, you should understand how vibrations happen in crystals, how we classify different vibration modes, and how these vibrations affect thermal properties. So we have three things. And you should also be able to distinguish between a simple monoatomic crystal and a crystal with two atoms in the repeating unit. So we have monoatom or multiple atoms or two atoms, two types of model. And later we will connect the vibration picture to the quantum idea of phonons. And finally, we will see how the Einstein and Debye models help explain heat capacity. Heat capacity. So this is one of the properties of materials. The chapter has very clear flow. First, classical vibration, then branch behavior, then quantum interpretation, and then thermal consequences. So if you keep that overall structure in mind, the chapter will feel much easier. So the first, classical vibration, and branch behavior, then quantum interpretation, then thermal consequences. Now look at this one. Let's begin with a basic question. Why do we even need to study crystal vibrations? What is so important about that? The answer is that these vibrations affect many real material properties, as I mentioned before, thermal, the optical, whatsoever, and whatnot. For example, when heat flows through a solid, lattice vibration plays a major role. When sound travels through a solid, that is also related to atomic vibration. Even the heat capacity of a material depends strongly on how atoms vibrate. So this is not just a theoretical topic. It is directly connected to real material behavior. A useful mental picture is to imagine atoms as small balls connected by springs. If one atom moves, it pulls or pushes the atoms next to it, and that disturbance travels through the crystals. So that simple picture will guide us through most of this chapter. Before we go into the crystal models, we need to understand the two basic types of wave motion. The first is the longitudinal wave. In this case, the atoms move back and forth back and forth at the same direction as the wave travels. The second one in the slide is the transverse wave. Here the atoms move sideways while the waves move forward in another direction. The atoms move sideways or like this, while the wave moves forward or another direction. It's a transverse wave. Longitudinal wave, atoms move back and forth the same direction as the wave travels. But the second one is transverse wave, where the atoms move sideways while the waves move forward or another direction. So we have longitudinal and transverse. So this distinction is very important because different vibration modes in solids can behave differently depending on directions. When you look at the diagram, please focus on the direction of atomic motion. Do not worry about the exact shape of the drawing. The main message is very simple. Crystal vibrations are not all the same. Sometimes it is longitudinal, or sometimes it's transverse. Some involve motion along the direction of travel, from here, from left to right, or from right to left, and some involve motion across it. The wave propagates to the forward, but the atom moves left and right or sideways. Now look at this one. We start the simplest possible crystal model. We assume a one-dimensional chain made of identical atoms, just like my drawings this morning. Okay, one long chain, linear chain, one-dimensional linear chain made of identical atoms. Atoms are connected. Identical atoms are connected. So each atom has the same mass, and the spacing between atoms is same everywhere. So we assume each atom mainly interacts with its nearest neighbors. So this is a simplified model, but it is extremely useful because somehow it lets us to understand the main physics without too much complication. So in physics, we often begin with a simple model first, then move to more realistic cases later. So at this stage, just imagine a repeating line of equal atoms connected like masses and springs. This is our starting point for understanding lattice vibrations. We have the equation of motion set up, but never mind. Please don't mind about the equation, just to show you how the equation looks like. We focus on more important things. Alah, ada yang dispersion relation tu tak nampak ke bawah? Nanti saya betulkan dia, dispersion relation tu. Saya betulkan dia. Saya buat tu. Ya, betulkan dia lah. Right. So now, this slide introduces the equation of motion for the simple atomic chain. I do not want you to read every symbol. Instead, focus on the physical meaning. Don't read the symbol, the complicated equations. Focus on the physical meaning. So the idea is that each atom feels a restoring force due to the atom next to it. Restoring force, meaning that just like a spring, if we stretch a spring, there will be a restoring force that pulling back the string to the original position. If we compress a spring, just like the spring of a car, if we compress a spring, there's a restoring force that tries to oppose the motion of the compression. So the motion of one atom depends on the motion of its neighbor. If we assume the disturbance travels through the crystal like a wave, we can derive a relationship between the vibration frequency and the wave pattern. And that relationship is called the dispersion relation. In simple words, the dispersion relation tells us how the vibration frequency changes when the wavelength changes. Remember the graph omega versus k this morning? This is the one. This is one of the key ideas in this chapter. So, believe me or not, Proton in 2009. Proton, perusahaan automobil nasional Berhad. Proton, bukannya power window rosak, oh no, oh tidak, oh tidak, oh no. PR, power window rosak. OT, oh tidak. ON, oh no. Wah, bukan. Bukan that Proton. The perusahaan automobil nasional Berhad. That one. Now, Proton now is getting better already because few years back, in early 2000, Proton kenal dengan apa power window rosak, but nowadays no longer that kind of issues lah. Proton. Jangan kutuk-kutuk Proton lah. Tak baik. Alright. So, believe me or not, in 2009, we have an interview session with a PhD, with a man, Dr. Anwar Alias, if I'm not mistaken, that was his name. If I'm not mistaken, this is the staff of Proton, and he works in the R&D department where he needs to design the absorber, the spring and the absorber of Proton car. During that time, I think they are designing a Inspira or the brand new Persona, I can't remember, but new type of Proton car. He's the one who's designed the spring, also the absorber, and believe me or not, he uses this equation. He uses quantum mechanics, he uses the solid state physics relation. So yeah, surprisingly, Proton, one of the best car that has the best handling. Proton car handling, Proton, I have no doubt about it. Handling, very good. Proton. If you want to compare with the other brand, the other Pro brand, so Proton's handling much better. So he uses the concept of solid state physics. Okay, so remember we have the omega versus the K. That's how that is the dispersion curve. Okay. Tengok slide seterusnya. Yep. Nanti dispersion relation tu saya tunjuklah, yang hijau tak nampak, nanti saya baiki. This is the dispersion curve graph. Look at the dispersion relation in graph form. This graph is very important because it gives a much better physical picture than the equation alone. That's why I say don't look at the equation alone, look at the picture. Understand the bigger picture. Near the center of the graph, the curve is almost straight. Tengok center balik. Tengok center, right? The curve is almost straight. That means for long wavelengths, the vibration behaves in simple and familiar way.